This is the River Bollin.
It has its source above Macclesfield Forest in the Peak District and has its confluence with the Mersey and Manchester Ship Canal near Lymm. The total length of the river is 35 kilometres.
Today we are aiming to investigate whether 4 key river characteristics of Bradshaw's model can be identified in this river. Bradshaw's model suggests that there is a pronounced increase in width, depth and discharge of a river from source to mouth, and only a marginal increase in river velocity.
We can formulate hypotheses from the same. The wetter width of the river increases from source to mouth. The average depth of the river increases from source to mouth. The velocity increases, but only slightly, from source to mouth. The one we are going to do is the discharge, as measured by velocity area methods, a British standard 3680, increases from source to mouth.
We have selected 3 sites on the River Bollin to investigate. These sites were sample based on a stratified sampling technique. This means we can get data that spans the different parts of the river. We will have a sample site in the upper course, the upper to middle course and the middle course. If we had selected sites based on a random sample, it might mean we won't have a spread of data or see any changes, so we would not be able to effectively test our hypothesis.
Here we are at Langley, which is the upper to middle course of the Bollin. It is just downstream of 2 reservoirs. The site was chosen as it is a small field study centre, so the access to the river is available to us. It is on private land, but we are not trespassing. The fields have no livestock in them. As it is downstream of the reservoir, the depth of the river is such that wellies are fine and it will be safe for us to get in.
Here we are at a tributary of the Bollin in the upper course. This site is also within the land of the Field Study Centre, so again it is safe and easily accessible.
Here we are at the Cars Country Park at Wilmslow. The site was chosen because there is ample place to park close to the river, so we don't have to carry equipment very far. Also, we can have complete access to the river as it is a country park and open to everyone. This part of the River Bollin is not too deep, so it is safe to take measurements.
Measuring the velocity of the river. Here we are measuring the velocity of the River Bollin. This will give us data to use to calculate the discharge using velocity/area methods, a British standard BS 3680. I have measured the wet width of the river and divided this measurement in 3 to form a systematic sample of sites across the river. At these 3 points I will measure the velocity.
This is a flow meter. It has an impeller which goes into the river water, pointing upstream. It is placed in a depth of 1/3 of the river. This allows the impeller to move freely and measure the river velocity rather than the surface velocity.
The impeller has been put in the river, and you can see the type 1 is standing behind the impeller, which means that there is no effect on the measurement. We are not creating any turbulence which will negatively affect the accuracy of our reading. The number on the click meter is recorded. A minute is timed by stopwatch, and then the finished number on the clicker is recorded. 3 recordings will be taken at each site and an average calculated, which will be used in our calculations of discharge.
Out the way a bit.
Yeah.
1, 2, 4, 1, 3, 4. 1, 2, 4, 1, 3.
This is lunch at the Field Studies Centre.
Here we are in the classroom. We have the start and finish clicks, and so we are calculating the number of clicks per minute for each of our sample sites.
Let's refer to this calibration chart, which is secondary published data, to convert the number of clicks into velocity into centimetres per second.
I have a measurement of the wetted width in metres, and whilst out in the field I measured the depth of the water at the systematic sample sites.
I have calculated an average depth from that data. If I multiply the average depth and the width, I will get a figure for cross-sectional area.
At Wilmslow, close to our third site, is a gauging station, 17 kilometres. Its average discharge is 1.275 cumex. We can compare this published or secondary data with our fieldwork. This allows us to check for accuracy, and we can use it on our scattergraph as well.
Here we are back in the classroom. We have put the data into Excel and created a formula to check our calculations of cross-sectional area and discharge. Using Excel, I can create a scattergraph of depth, width, discharge and velocity over distance.
On a scattergraph, the independent variable, the distance, is on the x-axis, and the dependent variable, the discharge, is on the y-axis. For each pair of data, there is a point where the discharge measurement and the distance measurement meet. I am including my secondary discharge data in this.
The benefit of the scattergraph, and particularly the trend or best fit line, is that it is possible to use the data to show a trend and the strength of a relationship. If the points are close to the trend line, your relationship is strong. This scattergraph with trend line is completed using Excel, and here it is possible to see that the relationship is strong. It shows clearly that discharge increases with distance downstream, and by looking at the axes it is possible to say that it increases quite significantly, thus supporting Bradshaw's model.
Also, should we have used the secondary data on the same scattergraph? Possibly not, but the conditions we have experienced were similar to average, and the secondary discharge data is in average for the Bollin at those locations. So on balance, it helps me more than hinders, but also for Wilmslow, my results were not very different from the gauging station, and that gives me some confidence that my results and data collection is accurate.
But there isn't much data here, and this is the downside. It is hard to make generalisations on such a limited number of sites, and it would improve the study if I was to introduce more sites into my study. However, access to the river as it flows through private land is difficult, and also the further downstream, the deeper the river, and so the fieldwork could not take place because it would be too deep for wellies and therefore dangerous.
Why have you chosen this method? Why have you not used a float, which you time over a known distance, say 10 metres, and then repeat it a few times to get an average?
Using a float is an acceptable way to measure velocity. Many people do it that way if they don't have a flow meter, but the float can get trapped in debris or turbulence in the river, which gives a false timing.
Using a float is time consuming as the method needs to be repeated several times to get a median value.
But most importantly of all, a float is measuring surface velocity, which is subject to friction, and so it's not as accurate as measuring the river's true velocity, a third below the surface.
So are you saying that the float here is more accurate?